Hello, ladies and gentlemen. I am Dr. Tina Burns. I'm your professor for this class, and we're going to go ahead and review lecture. I'm sorry, we're going to go ahead and step into lecture B. This is the second lecture in week 6 for the summer of 2025 for computer architecture, or CS211 for Rutgers University. Now, we're going to do today is we're going to do a few things. We're going to review locality. Now, we talked about that in the last lecture, and I believe that's where we ended. And then we're also going to look at some cache data flow examples. Now, we talked about that a little bit last time, but we're going to go into more detail about this. And we're also going to look at doing some sample hit and miss rate calculations. And we're going to do a review of data type, memory types. Now, we talked a little bit about memory types in the second week of the class, but I wanted to review it a bit more in detail because I know that's coming up for your upcoming recitation. So I wanted to do kind of a refresher, a reminder on that. So memory caching. There's a few elements that we want to consider and remember when we're talking about caching. One, um, anytime you refer or you look at a memory address for an array, it always starts at the beginning, the first element in that array. So anytime I want to look at an array, you notice how when we're looking at assembly code, it always said, hey, start at this address, and then we're going to add a certain number to it in order to get to whatever the next element is. And that's going to be your general reference and generally kind of how you see those things. When we look at storing data, the size of that data may vary. Um, we already know that if you're dealing with an integer, it's going to be 2 to 4 bytes, depending on the system that you're in. And then as you deal with floating points, they're going to be a little bit larger, long, shorts, right? And then depending on an array, that can be a myriad of sizes depending on what is being input into that data. Now, the thing is, if you are dealing with cache memory, and if you have a data item that's too large, like let's say you have an extremely big array, right? Or you have just a lot of data in there, it's not going to be stored in the cache. What you may have is just kind of um, the first array, the first element of that array, or you'll have a reference to it. When we look at an example in our modern world, a lot of times we think about cache, we're thinking about caching, we think about websites, right? So for websites, you're going to save the copies of the websites and you're going to include all of the data like the images, script files, and HTML information, right? So that's one example. And it allows us to decrease loading time because if I can keep all that data, then I don't have to worry about constantly pulling it directly from the source, but I can keep that stored in the local cache memory of my browser. All right, so that's kind of our what we thinking about when we're looking at cache. But let's go a little bit more into locality. Now, locality, as you guys remember, there's two forms of it. We have temporal locality, which is going to store those frequently accessed items. It's going to make sure that it keeps those close. It wants to for that, you're going to want to make sure that you're keeping that information very close to you, and it is going to be based on time, right? It's not going to be based on space, but it's going to be based on time. And an example of this, as we saw, is this, right? If we look at it, let me go ahead and pull up my annotations here. I really should keep I don't know where. So I changed my view of this a little bit. So now I'm wondering where my annotations. Oh, here they are. All right. All right. So as we look at this item is accessed 3 times within this span, right? That means that more than likely I could store this element if I'm prefetching, I could store that, and I would store that if I'm using something like temporal locality. Prefetching means you're going to get that data before or keep it before you know that you need it. So that's what we call prefetching. Now, this is going to be based on time. Spatial locality is going to store the addresses that are close together, and this is based specifically on location. So we'll see that this is an example where you notice that it has 800, 801, all of those right next to each other. So what this does is it's going to prefetch that data and say, okay, I have 800. Let me go ahead and load 801, 2, and 3, and 4. Since those are really near it, I'm going to load these data items as well in an effort to reduce cache misses. I will preload that data or prefetch that data to kind of save space, to save time, and make my cache a little bit more efficient. Now, this does become an interesting dilemma when you prefetch this data, right? And you have the danger of saying, okay, how often am I going to do this? How often am I going to keep on loading data if I'm not sure when I'm going to be using it, right? And that's going to be up to the design engineer in terms of how you want to load that. It could be, okay, maybe I only prefetch data on the first iteration, the first call of the program, but after that, I don't do it. Maybe you want to do it more often. It depends on how you want to design your cache and how often you think you're going to be accessing that data. If you know you're working with a lot of arrays, maybe the first time you access an array, you want to say, okay, anytime I have an array, what I'm going to do is I'm going to prefetch this data and just get the next 5 elements of that array so that I can store that and have that information. All right. We talked about as you're looking at this data and prefetching and all that, we talked about the different elements of a cache, right? Layer one cache is our lightning fast cache. That's going to be the one with the quickest access. You can get to that a lot faster than the other ones. It's going to be the smallest cache and also the most expensive. And it's going to be the one that is closest to your processor. That's going to be the cache that's closest to your processor. We have the level 2 cache, which we call the bridge. And the reason we call it the bridge is it's because it's between, as is indicated, it's like sandwiched between the layer 1 and layer 3 caches, where it allows a access to the data, right, to having an additional amount of data, but it also is relatively fast, not as fast as the L1 cache. It's slower than the L1 cache, faster than the L3 cache, and provides this intermediate bridge between layer 1 and layer 2 cache, right? Or level 1 and level 2 cache. Now, for the level 3 cache, this is often known as a shared resource, and it's accessible, for example, by multiple cores. So it's a good way to share information among multiple cores, especially when you're doing some multi-core processing. You can just kind of attain and get information from here. It may be used across different levels as a good sharing resource in order to gain that information, which would allow you to handle tasks a little bit more quickly when you're in these multi-core processing um, actions. Now, here's an example kind of this pyramid that you're going to be used to seeing um, where we have what we want to call L0, right, is your registers. You could really think about that like your your processor, right? Looking at this guy right here. This is meaning like, okay, this is going to be our processor. Then we go down to this L1, and that's going to be that level 1 cache that's in between your CPU, right? So this top one is going to be go from the CPU down to where you would have kind of like this uh main memory here, right? They label it as, L4, but really it's your main memory that you would have here, and then those other three caches that are in between. Now notice how as it goes down in these sizes, so this is our CPU up here, right? CPU member. Notice how as it goes down in this pyramid, it gets slower and slower in terms of access, but each of these becomes cheaper and cheaper and cheaper, right? So this, when we do it, for example, with web servers, and this kind of secondary storage, we're accessing a massive amount of data over the web. So this is going to be huge, huge size as compared to, for example, your level one cache. It's going to be sometimes a little bit slower to access, but it's going to be a lot cheaper, which is what you want because you need a massive amount of data here. And as we said here, your level one cache is going to be quick access, very fast, a good amount of speed. Now, what you want to notice, and I don't think we talked about this last week or last class, is that your level two is going to store information from the level three cache. So in your data flow, I might want to say, hey, let me pull this memory. Is it there? No. Okay, let me go down to here. Is it there? Okay, if it is there, I can now go back up to hit this and get it up to where I want to get it for the CPU. If I did not do that, right, if I did not store this information from the L3 cache, then I would still have to go all the way down to this main memory. So you want to make sure once you have it, you store it. If you have this three-level cache, what you want to do is make sure you store the information in this L3 cache. So once it's accessed, okay, I can then store that in there. I can store the data that is from the main memory, and that makes it easier to access it overall. Okay. Now, here's something we haven't gone over. Um, you know what I realized is that I probably could did a better job with these arrows, but all right, we'll keep these there for now. Um, when we deal with these, this is the memory mountain example. Now, of course, this is from my favorite teachers of this course, favorite course implementation from Carnegie Mellon. So a special shout out and thank you to Dr. Bryant and Dr. O'Halerion. I'm pretty sure I did not get that right, but it's fine. Thanks, special shout out to these professors. Or former professors of Carnegie Mellon University. So this they give a really good pictorial example of what we are discussing and how we kind of want to look at those items as we are fetching and prefetching, and we're talking about all these elements here, right? So let's take a look at this and kind of understand it in a little bit more detail. All right. So the first thing we see here is this is called a memory mountain. That means how am I relating or accessing, what am I doing with all of this information that I'm getting from memory? How does that look in terms of my read throughput? That's what's really going to be important. And in terms of your size overall. So our y-axis is going to be your read throughput, right? Um, and when we look at these, that it's gonna be oh, I'm sorry. I guess this is technically the z-axis. So let me just go ahead and write this out so that I'm not giving out misinformation here. Yeah, I'll keep Lou. So we have our this is our z-axis, which we call this is going to be our read throughput, which is going to represent how fast am I getting this information? What's the speed that at which my data can be accessed from memory? The faster, the better, right? The faster I am, the greater the more quickly I can get my information. That's what we want. We want speed, and we want access. Now, the x-axis, right, is known as our size here, right? So this is our x-axis. Now, our size, that means for each memory case, how big is it? How large is it, right? With it kind of increasing as we go from this, it's not really right to left as we go in this direction, it's increasing going in that direction. All right. And then we have our stride. Now, the stride is a new concept. We haven't really talked about that. And we're not going to focus on that, explicitly in class. But the stride is the distance between it's the distance in memory between consecutively accessed elements. Meaning my stride is like how many blocks of data am I using, right? Am I gonna have, if we're looking at terms of cache, is it gonna be eight eight blocks in this cache? Is it gonna be four? That's kind of what we talk about when we're looking at our stride, right? The row size of my elements. Now, with larger strides, that means you're going to be skipping over some memory locations. All right, so now that we know this, and we'll call this our y-axis, let's take a look. We can immediately see kind of what we're seeing in this graph, right? Let's take a look at it. We'll look from the bottom on up. This right here is our main memory. This is our largest memory, as is noted in here. Level 3 cache. I said we have. I'm so sorry. My bad. It's our largest size here, right? Looks like 128 megabytes, I'm guessing. Somewhere around there. And then when we go up here, we see this as is indicated for our layer 3 cache. It's about 8 megabytes in memory. So this is going to be our layer 3 cache here, 8 megabytes in memory. That's kind of where we're going to top out. When we go to the level 2 cache, this is going to be 256 kilobytes in memory. All right, so looking kind of around here, I'm guessing. I'm wondering if I could delete that. Yeah, let's go ahead and delete. Okay, so that's going to be a layer 2. Layer 1 is kind of be up here. That's going to be your smallest one here, right? So you see how that's kind of in the back of this graph because that is the smallest one. And then it goes out and expands a little bit further as we get down to these lower sides. But we also notice about this is look at the throughput. Look at the read throughput for this in megabits per second. As we look at this, the read throughput meaning your speed. How fast am I? Like how fast am I accessing this data? The layer 1, the level 1 cache is going to be the highest throughput. That's going to be your, not the highest throughput, I'm sorry. It's going to be, excuse me, your fastest speed. I can access this and get to this very quickly. As I go down and I increase inside, you can see a noticeable decrease in our read throughput until we get down to this main memory where the read throughput is extremely slow. So that's one of the first things we see in this in this kind of example. Now, what I also want you guys to notice is that which is why I really like this picture, um is that we can see what happens as we're accessing this. We can see what we call the ridges of locality, right? So spatial locality. Spatial locality again means I am going to prefetch data and keep data in memory that is close to my address of interest. And as we look at this for the spatial locality, that means I expect it to be, um, I expect it to have more information. Um, I'm seeing that as I prefetch this data, right, I'm taking up a little bit more space, right? I'm going back into this and because of that, I'm taking up a little bit more data when I have this, but I can see kind of these ridges, right? You can see spatial locality is kind of moving really along this kind of x-axis, right? Then when I look at the ridges of temporal locality, right? The ridges of temporal locality, that's going to be based on time. And we can see that over time, I can see kind of where these ridges, I can see them kind of going up and down with my throughput being increased as I access this over time, right? If I keep it in my cache, that it makes absolute sense because if I keep this in my cache, that means that every time I access it, if I do this over and over and over, my throughput is going to be very rapid because I have that now in my layer 1 cache, right? So that's where we kind of see these these ridges kind of from this example here. when we have for the temporal locality, if the size is small enough, um, then your access, your read throughput is going to be relatively high. Now, once you have when the size gets bigger, right? So as we go down here and the size gets bigger and bigger, we'll kind of see that is going to diminish a little bit in terms of the effectiveness of that. All right. And then when we talk about aggressive prefetching, that's if you're going to gain and you're going to get all of this information really very rapidly, then you have that and you might do that more so in the level 1 cache. All right, so let's clear all of that. Hopefully that made a little bit more sense to you. Just keep in mind this memory mountain and what all of it represents in terms of our levels of cache, and how fast we're going to be able to access and get the information here. Okay. Now this is what I wanted to get to, right? Not saying that I did not want to get to the other items, but I was really looking forward to showing some of these data examples with this. Now I'm going to do this a little bit differently. Let's say we have this, right? First, let's understand the problem here and what we are looking at. Um, Let me try this because this is the way I want to do it. I'm wondering if I can. I want to kind of uh get out of the speaker notes. All right, we're gonna try to do this. Nope. I'm gonna try to make this full screen. Okay, that's all right. It's a little bit better. Hopefully you guys can see it. Let me try to. Okay, there we go. All right, so let's say we have this example here, right? I have an LRU policy, and what I want to do is I want to be able to look at what that final value is when we insert this last line and determine what my hit and miss rate are. Now, for an LRU policy, that means, right, least recently used. That means whatever element I have not accessed in a while is being evicted. It's getting kicked out. Use it or lose it. That's what it's saying. Use it or lose it. So if you haven't been used or accessed in a while, you're getting booted out of here. So if I know that and I have a 4-way cache, which is represented here on this right-hand side, I want to know what does this look like when I have my last example, and I also want to know what in the world is my hit and miss rate. Your hit and miss rate are going to be vital in terms of performance. We talked about that, I think, last week in week 5, and we talked about it a little bit in the last lecture, I think. I don't know. Sometimes the lectures just run into each other. So I talked about it at some point. So anyway, we want to have the better our miss rate is, the better our hit rate is, excuse me, the better performance we have in the cache. So we want the hit rate to be as high as possible, or in other words, we want our miss rate to be as low as possible. So we're going to look at an LRU example. We're also going to look at the same problem statement in a FIFO example. All right. So I have over here, these represent, also, I just want to make a note that for these examples, I am ignoring all the header information that is used for a cache. Now, as you do your project, you want to keep that in mind that you will need some space, right? We went through this whole example about how you know you're storing it in the cache, right? You have your offsets bit, you have your index bits, then you have a tag for the memory. We're ignoring all that right now because we want to get the concept of where this information is stored as we look in the cache, right? So this is why we're doing it this way, just to kind of understand the data flow and to get used to determining the hit and miss ratio. All right, cool. All right, bet. So, um, okay. So we have if these are 20, these would be like 20 lines of code where for some reason I'm changing these variables as represented by here, right? So imagine these are 20 lines of code, and this is what I'm doing with the data. What we're going to do is we're going to go through the process of entering this information in, and live, we're going to go ahead and get the number of misses and also see where that final cache is. So the first few items are easy. B is equal to 3. C is equal to 4. D is equal to 0. Now, what I would say one way you can do this, if you're dealing with an LRU, one way to do this. Now, you guys can choose whatever way you want. The way I'm going to do this is I'm going to keep the numbers here as my counter. Now, the lines will incidentally match up with the lines on here. I'm going to keep this here as my counter. Right now, I have entered these 4 lines in. It's a 4-way cache with 4 different variables, but I have not had to kick anybody out. There are no misses because these are all new. The caches are originally empty. When I go to this next one, also not a miss because I have my data type already stored there. So I have it here. All I need to do is say, boom, this is your data. This is what it actually is. I set that to 0. So I am now at 5, right? I'm going to put this, because I'm dealing with LRU, I'm going to go ahead and put this in as my 5. All right, now let's go ahead and go to our next one. 6. Now, 6 is this line here, E is equal to 1. E is not in our cache, so then that means somebody's got to get kicked out. And right now, 2 is our lowest number or the least recently accessed element. So this is now going to become 6, and I'm going to make this my E is equal to 1 item, right? So this is least recently used. That was the least recently used item, which means that's the one that's going to be replaced. Happens to be that the next item, B is equal to 2, is not in here. I ended up just booting that out, right? Because that was the least recently used. So it had to get kicked out, which means now I'm kicking out another element. Oh, I'm sorry. Let me, my first miss was right here. That was my first miss. I'm going to this next one. B is no longer there. Now I have my second miss because it's no longer in the cache. So then my value here becomes B is equal to 2. And that is at my line, my access line of 7. All right, so that's my access line of 7. I have another variable here that I have not accessed either, which is F. F is going to replace this one, which is my access line of 8. And another miss for this. I feel like, did I miss something here? Was I supposed to have more misses here? Let's see. Those sizes are a little bit off, which is gonna bother me, so I'm just gonna make these all the same sizes. Has nothing to do with you. All right, so again, I believe that's my number of misses. Let me go back a little bit with this. So the first one, A, B, C, and D. A was not there. E was our first missed item. B was our second missed item. C was E was our first missed item. B was our second missed item. F was our third missed item, which I never put in there. Right? F is equal to 5. B, oh, okay, I got it. I'm right here. So F is equal to 5. It's going to be our third missed item, which we are going to put here. Got it. D is equal to 1. D is equal to 1. F was our third missed item, which, okay, I'm sorry. I got a little bit, I got so distracted. We're right here, line item 8, B is equal to 2. Line item 8, here's our second miss. When I get down to F is equal to 5, That is our third miss. Okay, F is equal to 5 is our third miss. And incidentally, it is our 8th line, right? The 8th time we access this. F is equal to 5. Now I have D is equal to 1. D is equal to 1. Now look at that. Is another miss because I just booted D out. So D is equal to 1 now goes here. And that ends up being my fourth miss for these items. And then the value of F is equal to 3. Right? So this is my cache, and hopefully we follow through kind of what those misses were when we were looking at that. F is equal to 3, D is equal to 1, I'm sorry, is going to be 9. I need to update that here. F is equal to 3 is 10. All right, so now we have kind of those items that we are looking at there. All right, let's do 16. All right, so these are kind of where we start out with the last axis of these items. D is equal to 1, right? We can look at that. D is equal to 1, E is equal to 1, B is equal to 2, F is equal to 3. So basically, if we ignore that, because we already had F here are the lines that are kind of stored in that cache. All right. So what you see here is I did this already before, so I'm just confirming that the solutions that we just did matches up with my solution that I previously did. But anyway, so we'll see all that. Look at the misses that we're at now. We have 4 misses, and this is our count. All right, 4 misses. Here's our count. We're going to go on with that, right? So this is for this first set here. We just completed this set. Lines between lines 1 to 10, we have 4 misses. Now we're going to move on to lines 11 through 20, right? So if we move on to lines 11 through 20, let's look at kind of where we are for these in-process items here, right? I started out with here. Now lines 11 through 20, I'm going to start out with this first line here. E is equal to 2. It happens to be in the cache. No miss there. But I do need to update my count to say, hey, this is the item you just accessed. So, oh my goodness, stop it. So that becomes 11. C is equal to 3. C is equal to 3 is not in there, right? So I need to update something like that. I'm going to update with my lowest number that's in the cache. So now I have C is equal to 3. Okay, so we're again on line item 12. I'm updating C again, where C becomes 4. This is now line item 14, right? That is going to be the last one that was accessed. All right, so now I have this 15. F is equal to 0. That is going to be line item 15. You really are. All right, so we're already halfway through this, and wonderfully enough, we don't have any misses yet, right? E, C, and F, they are already in the cache. Great, fantastic, wonderful. Then we come down to, wait, did I get that number wrong? 11, 12, 13, 14, 15. Huh. I think my numbers are off. 10, 11, E is equal to 2, 12. C is equal to 3. E is equal to 2. Yeah, 11. C is equal to 3 would be 12. C equals to 4 would be 13. Oh, that's where my number was off. Okay. Just keeping the items here for reference. 14 is F is equal to 0. So now we're at line 14. Here's where we are. Line 15. For line 15, we don't have B in the cache anymore. So that means somebody's getting booted out. And the element that was least recently used was this one. So we're going to boot out D. So that means B is equal to 0. Would go here. This count becomes 15. This count becomes increased to 5. B is equal to 0, B is equal to 1. Now this count is 16. I just accessed that. All right, B is equal to 1. 16, 17. A is equal to 2. Again, I don't have A in my cache here. So what am I going to boot out? I'm going to boot out this guy. And we're going to make that A is equal to 2. We're going to increase our miss rate here. And this becomes 17. All right, so just to make sure we're here, 17, this is our 17th line item, right? And I ended up replacing that right here. F, we have that. So F is equal to 2. That is our 18th data access item. So that's how we're going to integrate that array. I mean, that's how we're going to integrate that in there. No misses there. C is equal to 1. That becomes 19 right here. All right, because I have just changed that number. And then A is equal to 3. I feel like I missed a number. I feel like this should be 7. All right, let me go back. Okay, so here's just where we ended up here. All right, is our in process. Sorry about that. Let's take it back right here. This is the end of our first 10 lines. We're starting here again. We know we had 4 misses here. We're starting here, 6, 7, 8, 9, and 10 at line 11. E is equal to 2. So E is equal to 2. That means this is going to be 11 for our access point there. C is equal to 3. We do not have anything for C is equal to 3. That means we're going to boot this guy out. Once we do C is equal to 3, this becomes 12. This is updated to 5. Now my miscount is 5. This becomes 12. It's also going to be 13 because C is going to be equal to 4. All right. So now we're at line 13. F is equal to 0. This is going to be my line item 14. All right, F is equal to 0. B is equal to 0. If I go up here, no B's here, no B's, no B's. Last item that was accessed is here. B is equal to 0. My miss rate is now 6. All right, I know that B is equal to 0 here. Then B becomes 1. B is equal to 0. I need to update that here. B is equal to 0 is my line item 15. 15, actually, we're going to make that 15 and 16. My count now is 16, right? Because I accessed it here, I accessed it here. Now we're at 17. A is equal to 2. A is equal to 2 is not in our cache anywhere. So somebody is getting kicked out. And it looks like it's going to be this guy. E was that has the lowest number. So we'll put our A is equal to 2 here. Update our miss rate to 7. That's where it was. That's where I missed it. This is data item 17. All right, I know that that is data item number 17. 18 is F is equal to 2. 19 is C is equal to 1. 20 is A is equal to 3. And that's how we end this, right? This is what our cache looks like at the end once we execute all of these items. And for this particular instance, we had 7 misses. And then here's kind of where our count was at the end of our data item, right? That's where the count was when we finished. So let's see what that looks like. Yep, 16. Yep. Okay, these are identical. Again, I do this because I pre-did this, so I wanted to make sure the solutions we had here matched up with what we had previously, and they do, right? So now we see kind of what we went through that on that example. Let me I'm going to just update this now. So the next time I do these slides, I have this here already. It's for my own reference, not for yours. All right, we're gonna delete that. All right, so this is where we started. This is where we ended. We'll do that one more time also for this guy. Hmm, that is not exactly what I wanted. Okay, this is gonna be a process one. Sorry, I'm just updating this for my reference here. We'll take that, put that right here. All right, so now we got all those. So this is where we started. This is where we had at the end of our first 10 lines, four misses, with the data that looked like this. We went through kind of this process where we changed it, and our final one is 7 misses where we went through the other line items here. So now let's look at how we can, from this, how we can calculate the miss rate. If you remember from our previous classes, when we look at the miss rate, we can easily calculate that by taking the number of misses and dividing them by the total number of content requests. For us, that's relatively easy. We already said that our number of misses was 7, and our total number of requests for this example was 20. That means that my miss ratio is 0.35. Or another way to put that is the miss rate is 35%. So 35% of the time, there will be a cache miss each time this runs, right? So that's one way to calculate it. And then there's also determining what the hit rate is, right? So this is my miss rate. What's the hit ratio? Well, the hit ratio is going to be 1 minus the miss ratio. So I know that it's going to be 1 minus 35, or my hit ratio is 65. In other words, the hit rate is 65%, right? So that's one very easy way to go ahead and calculate what the hit and miss ratio are going to be for those particular examples, right? Let's do another example. Now, this is the same example. It's going to be the same um, set of calculations that we did previously, right? If we look at that, just want to make sure. No, it is not. A is equal to 3. A is equal to 3, C is equal to 1, F is equal to 2. I'm just double checking for my own reference here. Yes. Okay. So these are the same numbers, same examples. So let's go ahead and exit full screen, or exit the presentation. If I go down here now and I calculate this, now instead of me using the least recently used policy, we're going to do FIFO. And FIFO is not like, hey, if you're not being used, you're getting out. FIFO is, hey, there's some seniority here. If you've been here the longest, then you're gonna stay here for a little bit, right? It's like tenure. Once you're here, you're gonna stay here for a while, right? First in, I'm sorry, nope, 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 nope. I'm thinking of Lilo. I'm sorry. That is not the case. It means if you've been here for a while, you're getting kicked out. I don't care if you're getting used or not. If you've been here too long, it's time for you to get up out of here. All right, so that's your first in, first out replacement policy. So let's go ahead and take a look at how this looks in this particular example. Our first set of lines are going to be the same. A is equal to 2, B is equal to 3, C is equal to 4, D is equal to 0. Boom, great. And the numbers are going to be the same. 1, 2, 3, 4. Actually, we're going to do this differently. I'm not even going to put any numbers here. I'm only going to put numbers in for the item that had a miss. Because I don't need to keep a counter for every single thing that I'm doing. So in the least recently used option, I had to keep a count of everything that I was using. But for this one, I only need to keep a count of what is the first element. And I can see that here, right? I can only need to keep the sequence of the elements I'm changing in this array. You'll see what I'm talking about as I go on, because probably did not make sense. Anyway, A is going to be 0. I don't need to replace anything because A is already there. E is equal to 1. Boom. Here we get our first miss. E is equal to 1. That is at data item or line 6. Line 6. I have my first miss. Let's go ahead and track that. Line 6. E is equal to, what did I say it was? E is equal to 1. All right, we had our first miss there. B is equal to 2. Not changing anything there. That remains. F is equal to 5. Okay, there's another one that, and another one. We don't have that. So now we have our second miss here at line item F is equal to 5, 8, I think. Sure, we'll go with that one. Why not? F is equal to 5 here. I'm booting out D because keep in mind, I don't care who's been there before. I'm going in order with the element that was in there first. That means from a point of view of the array, which element, which variable that I store first, that's the variable that is being kicked out. You're always just moving sequentially. You're just going from the top to the bottom. When you're done with that, you go back to the top. That's what makes FIFO a little bit more easier to implement because you can think of it like an array. You go through the array. Once you get to the bottom of that, then you go back to the top of that, and then you have your you have kind of your value for what you're going to be increasing. All right, so what you're going to be changing. F is equal to 5. That's my element 8. What's my next one? D is equal to 1. Now D is equal to 1 is still there. So I don't have a miss here. I just update the number. F is equal to 3 is still there. I don't have a miss here. Update the number. Now, look at the difference between this already. Using a FIFO policy, I only have 2 misses in these first lines. If we go back to the previous example, when I got through these first 10 lines, after the first 10 lines, I had already had 4 misses. So right now, as we look at the FIFO policy, we're getting half of the misses that we were getting with the LRU policy. Oh, you know what? I was not supposed to be updating that one. It's cool. We're gonna make it work. We're gonna just swap that around a little bit and take that out of here. Put that down here. Boom, we're good. All right, so we start out with 0. Now we're kind of in this process where we have these items, and look at this. We have 2 misses. We're already to the end of this. All right, the last item we put in here was this F is equal to 3, and we have 2 misses. Fantastic. Let me look at the solutions just to make sure we are in alignment with those same, yes, haha, same data in both of them. Excellent. All right. I'm going to continue with this in process 1 just because I think it'll make it easier. I'm going through these next 10 lines, right? Lines 11 to 20, starting off just with 2 misses. This is where we ended up. Okay, now we have E is equal to 2. E is equal to 2 is already in there. So we just need to update that. C is equal to 3 is in there. C, the variable C is there. We're just updating it to 3. And then we update it to 4. F is equal to 0. F is already there. We're just updating it to 0. B is equal to 2. B is equal to 0. Ooh, we don't have this one. Well, I guess that's going to be a miss. So let's go ahead and increase our miss count to 3. And the item that we're looking at is B is equal to 0. And that ends up being line 14, 11, 12, 13, 14, 15. So that's going to be our line item 15. All right, B is equal to 0. All right. Then we have B is equal to 1. Same memory address. A is equal to 0. A is equal to 2, excuse me. We don't have that, which means this one now becomes was that really 15? 16, 17. Okay, 17. And we are swapping this out for A is equal to 2, right? And I think did I increase the miss ratio for that? Oh, and you know what? Here's a good way to see that. I have 4 things here. So yes, my miss ratio does increase. It increases to 4. That makes sense. Hmm. Oh boy. All right. We're here. A is equal to 2. Okay. A is equal to 2. I have now my 4 misses. Next one, F is equal to 2. No miss there. It's in our cache. C is equal to 1. We do not have that there. Sorry, I'm just gonna check one thing really quickly. All right, I'm gonna do something. Let's take this back a couple. I'm gonna take it back to where we were at 2 misses, right? Last item, D is equal to 1. Okay, let me just take it back. I want to just make sure I'm doing this right. D is equal to 1, F is equal to 3. This is the end of our 10 lines. We're starting at E is equal to, or whatever the case may be. F is equal to 3 here. E is equal to 2. E was already in our line item here, so we changed that to 2. No misses there. C is equal to 3. C is equal to 4. F is equal to 0. B is equal to 0. Okay, that is where we need to figure out where we're going to change. B is equal to 0, which is what we're going to replace this line with right here. Our miscount then is 3. B is equal to 0. Our miscount is 3. We're right here. B is equal to 1. All right, so we're moving on to this line. Now, we're going to do something where we're replacing, by the way, that happened when we right here at our line item of 11, 12, 13, 14, 15. Line item 15 is where we replace that with 0. 16 is where it became 1. 17 is A is equal to 2. That's going to be what replaces this here. So 17, A is equal to 2, is going to replace this value here. Right? Because this is our line item here. Okay, now we have F is equal to 2. Our miss rate then becomes 4, right? Because now I have 4 misses here, I think. All right, so I have my 4 misses here, right, which is indicated by this count here, and I have A is equal to 2. I get up here, F is equal to 2. Great, F is equal to 2. Ba-da-da-da-da-da-da-da-da. 18, C is equal to 1, which means C is no longer there. I'm going to have to replace something. I'm going to go back to my first element since these are all full. I'm going back to my first element here. This would be 19. C is equal to 1. It's going to replace that. All right, once I'm down here at my first item, I'm sorry. Man. Ooh, this is rough. Uh, my changes are going to be 5 here. All right, once I have 5 here, C is equal to 1, A is equal to 3 is already in our midst. So we have 5 misses, all right? And again, I just went through that to make sure that I was right and we had our initial value all correct here. 5 misses for this guy. Started out with 2 when we did our first 10. We had 5 when we continued. Now that we have 5 misses, let's go ahead and calculate what that means in terms of rate, right? So the number of misses divided by the number of requests will give us our miss ratio. If we take 5, we divide that into 20. It's basically gives us 25% miss rate, right? Which means that for a FIFO, the FIFO implementation of this ended up having a better miss rate than our LRU replacement policy. If our miss rate is going to be 25%, that means that our hit rate is going to increase to 75%. And that is kind of where we end up for those, right? So this is a good way to kind of think about and going through these examples. I went back and I went through them a couple times just to be sure that I understood it. I would advise you, if you're listening to this lecture, you want to do those examples without looking at my notes. Do those examples 2 to 3 times. Make sure you have the same response because this will be on your final. You'll have a similar question on the midterm, but it's not going to be exactly that. But this will be a problem on the final. So heads up, this is going to be a problem on the final. So get used to this format. Hey, what does this look like when you end it? What are the misses? What's the hit and miss ratio? That will be a final exam question. Okay, fantastic. Okay, we're going to shift gears for a little bit. I'm actually going to take a short water break and then I'm going to be back. All right, so let's move forward. Let's talk about memory management. Now, as we stated before in a previous class, memory management is helping you to control and coordinate your computer memory. So all that we're dealing with when we talk about this cache, hit rate, miss rate, all of it involves how often I'm accessing the main memory or what I'm doing with specific memory addresses. So understanding memory is really essential for you to have a good program that executes well and rapidly. Now, this includes the allocation and deallocation of memory. Global memory is going to be something that's declared outside of a function. It's accessible from any function within a program. You can retain the value throughout the program's execution, and it's always allocated when the program starts. So that means that whereas we have these dynamically allocated addresses like something for when we use the malloc function. Global memory means as soon as you start the program, it's going to be allocated. For your stack memory, it's a little bit different. Okay, and it's deallocated when the program ends. Your stack memory, that's going to be memory that's exclusive to and only used inside of a particular function. And it's used for anything that you're dealing that has static operations, right? This is something that you're not going to need to change a lot. And you may only need it inside of a particular function. So this is going to be the last in, first out manner. Um, and this is something that's automatically managed in memory. The memory will deallocate this once the function has stopped running. Same thing with your program. Your program will automatically deallocate the global memory when the program stops. So the difference between the global and the functional is stack memory is for something with inside a specific function in a program. The global memory is going to be something for the the program overall. For your stack memory, it's going to be deallocated when the function is finished executing. For your global memory, it's going to be deallocated when the program is done. Heap memory. Now that's the one we uh, have the most trouble with because heap memory is something that is uh, it involves like the processor's memory, and it's used for dynamic memory allocation. So if we don't know the size of the array, if we don't know what the elements are, if we're getting something from a file or from a user input, we're going to be using this heap memory. And what happens is that it has a dynamic size, meaning that it can have its size can vary depending on whatever the inputs are, and the things that you're going to use to access these functions are going to be the malloc and the free function as well as realloc in some cases as well. And your heap memory is going to be if you don't free then, as you guys have seen in some examples, what happens is you get memory leaks and you have problems in your program. You could, if you don't do it correctly, you could end up crashing some things as well. So make sure that you have a good understanding of what you are allocating, and when you're done with that variable, to be sure to deallocate it or free the memory that is being used by it. So your C variable types. We have global, we already talked about that, outside all functions, and all parts of the program can access it. Our heap memory, that's going to be dynamic. It's going to create a stack space, and you need to manually allocate and deallocate that. And if you don't do that correctly, of course, it can leak into other spaces. You have your stack memory, which is just something you use temporarily. So that's often allocated and deallocated by the program itself multiple times throughout the program, especially if you're calling that function at various times, then that's kind of when you would allocate and deallocate that particular memory. So let's kind of review these stack versus heap. Um, for your stack memory, it's going to be uh, faster. Um, when you access that for your stack, it's only going to be for local functions, whereas the heap is going to be like global. It has a little bit slower access. The size is going to be limited for your stack. It's going to be unlimited for your global. Your management for the allocation, deallocation for stack is going to be managed by the program. For a heap, it's going to be managed by you, the user. When you look at memory allocation, um, that's going to be automatically done by your program. We already said that. But for the heap, you need to do that. You need to allocate it. The resizing of your stack variables is not allowed. For your heap variables, those are allowed within certain conditions, meaning you have to tell it what you want it to change to. These are my sources right here. So we're gonna try to I'll show you guys kind of, let's run through and create an example for this. Um, I'm going to try to get out of that and let's go into our example here. I am already in, I'm already in iLabs 1. So, I like to open my three tabs. I know you guys work in CS, VS Code and all of that. I'm not going to do that today. I'm just going to do it here. Let's make a folder. We'll call this week 6B. We're gonna go ahead and access that. All right, CD week 6B, and then we'll CD week 6B. See if I can get this. Okay, got this a little bit larger. Great. Yeah, we'll make it that size. Okay. So let's go ahead and copy our make file into All right, 6B folder. All right, now we have our make file here. So let's go ahead and open our make file. And we're going to start a new program here. We'll call this, so I'm going to demonstrate this. Let's demonstrate this with a sample like grade calculation program. So we'll do grade calc. Let's see. We'll open that up. I'm going to automatically change my make file to have that grade calc. Let's save that. All right. Of course, we're going to know we're going to include our libraries. We're going to have our main function. Print f. So this is a program to demonstrate memory types. All right, let me print that out. Let's go ahead and return our function here. All right, so we can go ahead and save that. We're going to include our studio standard input output. We're going to include our standard libraries. All right, we have all these values here. We're going to include those standard libraries. All right, I'm going to set a global. For this global, I'm going to call it curve. I'm going to make it a float. And we're going to set that value equal to 5. Okay, so this is our global variable. Because I have set it right here, that means that any program inside of here can access it. Let's set up a function to calculate the grade. So I'm going to have this function return a floating point value. And we'll call this grade calc. Okay, so what I want to input in this is a floating point value for the total. And then I'm also going to enter a integer value for the number of assignments. Okay. And what I want to return, I'm going to make this a floating point value. I'm going to call this grade. This is going to be equal to basically your total divided by the floating point format of your number assignment. All right, so grade, I declare this inside. So this variable grade, this right here is a stack variable. It will be allocated and deallocated every time this function runs. Okay. And what I'm going to return is I'm going to perform some calculations here, and I want to return grade plus the curve. Now keep in mind that I've accessed this from this global variable that was already here. I didn't need to declare it again because this is at the top. So because this is at the top, I can already access this right here as my in my program. I don't need to send it in. This is a global. That means everybody inside of here can access it. All right, for my main program, what I need to do is I want to get some user input values. I'm going to have the user input the grades. So I'm going to say print f enter the number of assignments, and they're going to go ahead and enter the number of assignments. And I'm going to scan that in. So I'm going to declare an integer. We'll call this n, and that is going to be equal to, we'll set it off to 0. And then we're going to scan and get the user input for this. %d, and I want this to be scanned into our integer n. All right, cool. So now we're getting the number of assignments kind of input as our variable. We scan that in. The next thing we need to get is this list of grades. Now, I know that I'm going to have a certain number of grades, but I don't know fully what they're going to be. I don't know the size of the array yet until I determine it based on here. And I don't know what those values are going to be. So I have to dynamically allocate this, right? So now here's where we set up an array where we get float. Um, Float array is going to be equal to, now this is going to be dynamic. So I'm going to put my, trying to remember if I do it here or I do it at the end. I think I do it before. That's fine. Where should we put that here? Malloc. And then we have size of, oh, we're going to do n times size of our floating point value, right? Right. This is how we're going to allocate our array. I did not want to record that. That was interesting. All right. So this is where we have now dedicated or allocated our array. Excuse me. And now we kind of want to move on from that. So I don't actually think, let's try something. Let's not include that. Because we've already said it's going to be dynamically allocated here, I believe that we can just do it this way and kind of allocate it that way rather than declaring this as a, well, we'll do it all at once. We'll see. We'll see if this works or if it gives me an error or we'll see. We're just going to go through it. All right. So here's what I'm doing. I give this header printout. We don't really care about that. I'm asking the user to input the number of assignments. I'm setting up a variable. I'm inputting that into this variable n, and I need that in order to know the size of my array. Once I have that, right, I've dynamically allocated that, I'm going to go ahead and ask the user to enter the grades. Enter the grades for the students. And we'll go ahead and enter that. All right, once I ask him, I'm going to save this. Once I ask him to enter the grades for the students, I'm going to have to do a for loop that is going to be where int I, this we already know, we're super familiar with that, is going to be equal to 0. Then I want to say I is, we're going to run this until it's less than n. And then we have we're going to increment that, and that's going to be our for loop. And the way we're going to do this is just we're going to set this up into the array. Array at the value of I is going to be equal to, oh, actually, nope, because we're just going to be scanning the user input. Scan F from the user input. We're scanning this data into our array. And we're scanning this into each value at the integer of I. At the array of I. We're scanning that as a floating point value. Let me just make, so this is not a integer, but I'm scanning a floating point value. So let's just make sure we change that there. Then after I do that, so there's a couple ways you can do it. I can create another loop that will add these values, but I don't want to do that. I want to create an int called sum here. I'm going to create a floating point sum, and we'll make that 0. And every time I get this in, when I scan this, what I'm going to do is I am going to add, I'm going to add this to the sum. So sum now is going to be equal to sum plus the array that I've just gotten from that value. So now I have my sum value, makes it really easy to do. And then I can go ahead and run my functions here to do my grade calculation. And let's go ahead and input. The first thing we get for this one is the total. So we're going to do that as a sum. And the second one is going to be our n. That's going to be our number of variables. And we're going to set this up as float GPA is all right. Now I want to do something to kind of print out these values to say, okay, what is the one? Let's do something with the number that we had up here. Let's print out this. So print out, so we'll print out we'll put out grade curved, and we'll print out the floating point value there. And that's going to be GPA. And then I really want to just copy this. Great, it copied it. Fantastic. And the raw grade is going to be GPA minus our global variable that's up here. So that's going to be minus the curve. Okay? So here's what we're doing. We start out with this, just giving the user some information. We get the number of, well, this is what it's supposed to be doing in theory. Get the number of assignments. You go ahead and you enter, you set up this value for sum. You enter in the number of assignments. You want to scan in and get that from the user. You set up an array for the numbers, ask the user to input the numbers. You store that into your array. While you're storing it, you're updating your summary value here. And then what you want to do is calculate the GPA using our function here. Once it's calculated, we print that out to the screen, and we also give the user some information on what their raw value is of the grade versus what they get when the grade is curved. All right, so let's see what happens when we make this. Okay, printf. Okay, that's a simple one. So we're going to make this f undeclared first variable, which so when I fix this and that, it should fix this one right here. Now this is a double, so it didn't like when I did that. So let's go ahead and change this to the correct value. Oh, I need to do this as a memory address. Okay, so these are actually relatively simple to fix. So if I go back to my program, the first thing we'll do, this will fix 2 errors in one. That'll be that. That means it's going to find it. And when I scan this in, I need to scan it in and say it's going to be stored to the memory address of this. And it's going to be the same thing for these guys here. So let's go ahead and save that. Okay, now we just have one error here. Total GPA grade calculate equals sum. And what is this? The grade? Do you mean? Oh, that's a spelling error. That is my bad. So now, the other thing I noticed is, and we talked about that, I did not free my memory. So let's go ahead and free our array here before we end the program, just so we don't get any memory leaks. We're going to go ahead and free that. Let's go ahead and make that again. And then let's run this. What did I call that? All right, we're going to do 3 assignments. We'll do 3 assignments here, and we'll do 89.4, 92.1, and 78.3. All right, so you'll see kind of as it given the values, and you'll see that it gave the initial one for this curved score. And then after that, it gave you a value for what you would get for the raw data and also what it would get for the other one. Let's change this a little bit to clean this up. And let's make this %1, just because I don't necessarily care about all the other stuff that's in there. I'm going to do something here just also for my preference, in that I don't want to have this right next to the other one. I want to have a line item right before it. Let's make this again. Okay. Okay, 3 assignments, 89.2, 77.4, and 98.3. All right, so I entered those grades in. It gave me the raw grade and also the curved grade. So the program is functioning as we would expect, right? So let's take a look at that and just kind of look at where our variables are. I'm doing this so we can kind of have a little bit of a better understanding of what we're doing as far as memory and how we're accessing that and all that. Here is our global variable. This is something that is good to see. We notice that it's here. I can access it from this function. I can access it from this function. It is not deallocated until the end of the program. And then I have my stack variables, which are going to be this grade. That's going to be localized to this function. It's allocated and deallocated when that function is run. And then I have what's called this the main function. I include here something for my heap and my stack memory. I'm sorry, I'm including something for dynamic memory where I'm storing stuff into the heap values. So if I wanted to look at this, let's go ahead and create a assembly code S file for this. GCC -S keep in mind that that is going to be always your C file. Now we have our .s. So let's go ahead and open this up. Okay, so look at our information here. This is, we're going to title it. The first thing it's going to do is, as we're looking at this, is our grade calc. Look at what it's doing here. That's our first function. It's going to go ahead and get this kind of offset, take out information from the stack so that I have data and I can store memory into that variable here that we talked about for the floating point grade. Pop this out of the stack, you put the information in, and then you return kind of your RBP value, right? This RBP value is returned at the end of your function. Once you add this, you get all this information in, you're going to return that at the end of the function. All right, our main function, of course, we have, hey, these are my strings. Answer this, we already know, we're familiar with that. Let's get down to our main function where we kind of see some other things dynamically allocated. We're subtracting 32 bytes so that we can get some information here. Oh, you know what I did not do? We did not talk about look at this value, curve. This curve value, because it's not inside my program, curve is a global value that we see, a global variable that we see allocated and dedicated right here at the top of our program, right? As soon as we get this, we say, okay, this is a type of variable it is, and we know that it is it's a global that can be accessed everywhere. So I can kind of see where that is. I can align and get everything all lined up and ready to go. And then I have access to it in other forms and other areas of my program. Notice how I call it, and curve is already accessed here. So I declare it here as a global, and here is where I'm taking these to. I'm basically going to move that into XMM0. And then I'm going to add these two variables, right? XMM0 plus what the original value here, the 4 RBP. My 4 RBP was more than likely that division here. Yeah, okay, so I divided the numbers here, right? This division. And then what I did was I stored that divided value into the address of -4 RBP. So then all I do is I take this, I put that into the address of XMM0, I add these two numbers, and that's what's then output to the stack. So, but the point I wanted to make here is that your curve variable is stored as a global, and I can literally call that by name here. And we'll see that even when we access it a little bit later on in the program, we're calling out to this and we're just doing it from that access of curve, from the global variable. Here, of course, is what I talked about, this dynamic variable. I have all this information. I'm going to jump to this, leave the program, do all this and to return it, but I want to make sure that I free this. So I have this and I'm clearing everything from the stack once it's used. I'm freeing my variable here. That's kind of what we deal with our array function. So if we look at our main function here, you take information from the stack, you're getting data, you want to get this from the user somehow. You're calling this to plot something. The thing that you're plotting here is or you're doing the LCO, LCO here is this first line item that it prints out. After it prints out that and says, hey, this is such and such program, you're going to move this, whatever was an RA of X, you're going to go ahead and move that into your RD of I. You're going to output, that means you are, looks like you're setting up a variable to be able to use for your N. You're going to call this, you're going to ask them to, you're asking the user to input data for the number of assignments, and then you are storing that data for the number of assignments into RAX, and then you go ahead and save that into RDI to be used for later. And then the next thing you do is you are going to plot out and say, hey, can you now give us the information for uh give us the information for what the array is itself. And now here's kind of where we start dealing with the array a little bit and entering in and getting information from the array itself. All right. It tells you what that is, gets the information from there. Um, and then here's LC3. LC3 is where you're going to enter the number of assignments. Right. You say enter number of assignments, you store that into here, output that, and then this is kind of where we start that. Here is when we call in this malloc function, this is where it is taking that information and it's going to go ahead and allocate that, right? It's going to allocate that to your particular array. Once you do that, you say, okay, I've allocated this memory. Now we're telling the user, go ahead and input that memory. And here's where we start moving in data for this. And we keep on moving this. This is kind of our loop. Where we jump to L4. L4 is our for loop that moves and inputs data into each of the arrays. So this is a for loop. You compare it, well, you enter in the data into this for loop. You keep on comparing it. So this basically, it says that you're going to jump if you are less than, or if the information, if n is, if I is less than n, that's when you're going to jump to layer 5, which is the rest of the items here. But all you're doing here is you're just storing information into this function. Here we know this is where we call grade calculation. We have all the information. We're moving all the data here. And that's pretty much where we see kind of how we're using these memories. We're dynamically allocating all that data. All right, guys, that's all that I have for this class. And I will see you in lecture in the next lecture. Enjoy the rest of your day.